Hello everyone, this is a SAP2000 tutorial. In this tutorial, we're going to model and conduct a pushover analysis on an eccentrical brassed frame. So, eccentric brassed frame is a sort of brassing system or lateral resisting structure, which the brassing will not pass the beam central lines, but instead we will generate a link between two brasses. So here is a figure you can see. This is the brassing, and the brassing is not passing through the center of this midpoint, and instead it's going to generate a little offset, and it's called the length or arm. So during the earthquake, we expect this link part should damage instead this area. And if we go to the eccentrically brass, and you can see here there is no link or arm. So this is concentrically brass and this is eccentrically brass. So this is a very much more ductile and also complex than the eccentrically brass. So it's utilized for earthquake area with a high seismicity, and as well as for high-rise building, and this is a better system than the eccentrically brass system. So we will follow these steps. First we will model, and the second we will define a section. We expect the section is I section 200, and the beam, you can see the beam is about 150, and the brass is HSS or hollow structural section 100. We conduct pushover analysis. The pushover analysis, capacity design analysis or capacity analysis, which means the structure always should be designed, and just we want to evaluate the response during pushing or a lateral load. So the structure is already designed and confirmed, but we want to see how the capacity of this structure is, and we want to see the response. So for this purpose, we need to define some hinges, because pushover analysis and nonlinear static analysis we need to define. And the one of the simple way is defining hinge to the beam, column, and brasses. And the second method is using fiber element, which is a little complicated than the hinges. And then we will define a boundary condition. We assume the structure is fixed in the bottom, and we have loading, the second stable loading, and we want to define a dead load and a live load, 50 and 10 kilonewton per meter respectively. And then in case if we want to add some lateral load, we also consider a lateral load as a load pattern, and then we jump to the load cases. In the load cases we should define nonlinear static loading, dead load, live load, and pushover load. So then we will perform the analysis. We fix those parameters, which is effect analysis and the result, and then we will evaluate and see the pushover curve and the capacity curve. And also we can see the hinge response. So we jump to the program, we use SAP2000, and you can actually use any version you want. And here is the first thing you should fix. The unit is kilonewton meter, and you can use the material, which material you want, and you're using United States material. And here is 2D, so we're not expecting to use a 3D model. You also can do it, and for a simple steel we use 2D element. And 2D you can use portal, which is a moment resisting frame, and you can inside is called concentrically brass, and this concentrically brass you can see a X shape and an eccentric. So we select the brass and eccentric, and here is the information that regarding this one. So the expected story is 5 story, and the story has 3 bay, 1, 2, 3, exactly. The gap width is 1. It means that between this one is 1, so we expect the bay is 6 meters, so then it be 2 divided by 2 is be 1. You can change based on this ratio between these. If I suppose let's be 1.5, so it should be a little different, like 1 meter. So 1 is okay, that's good. And we also, in case if you want to change the grids, you can come here, but we don't. So now here we have to select define the beam. Later also we can keep a default, but we want to make simple, and here we want to import the type of section is I section, you can bring from your which standard you want. So you can use standard Europe or whatever you like. I'm using AICS14, and this is here. So from I section or W, I take 200. There is 201. You can see here. I'm gonna take a compact one, the last to this one for the column. And again, I'm going to back the same area. I'm going to bring it W150. Here's 150, the last one. This is the last one. And tube or SS. You can see SS here. And SS is 100. So I'm going to take the last part of the S100. Yeah, here is not available 100, so 101. Taking this last one, which is compact, 100. And okay, and the steel material is already selected. Steel A99, which has a 50 KSI yield strength. We also can actually modify later. So here again we select this is beam, and this is column, and this is brasses. So okay, we have automatically finished our modeling. I want to delete this window and just keep 2D model. And the first thing is I'm going to assign the boundary condition. As we already said, it will be fixed. Yeah, I should say that the length is here is 1, and that means the gap is 1 meter. So that I say the ratio is not considering the ratio is 2 and 1. So in case we can increase there, and that's it. I should fix this. And so now in my case, this should be 1 meter, not actually not 2 meter. So if I go to the grade here, edit grade, and you can see the grade is going to be, let me spacing, and the grade is 2.5 and then 1. So you can see between A, you can see A, A and B, because in that other it will be 1, 2.5 and 1, 2.5 and 1. So this length is 1 meter. We can extend as we expect. So the changing this is not difficult. So we can change the grade, and then we can model it simply. So as example, if I want to model, and I can go to the modeling part, and here is modeling, and I can select the brass it is, and select this node and this node, and this node to this node. So it's not a big challenge. So we don't need so we escape the modeling, and we want to now the restraint boundary condition is finished. We're going to define the load, but before that we have to define the section. We come to the Hinge properties, and we define steel column hinges. Column is a member which can bear the axial force, moment, and measure and minor and major moments. So we taking the interacting P, M2, M3, and there is any specification is 2 times, and you can consider the moment curvature. You also can calculate, and you can give the ASAP safety factor, scale factor for the rotational. Or the program use this equation from AAC41 and then give it to you. It's okay, let the program calculate for us. And you also moment curvature as well. You can we already have the column, and then we can determine the moment curvature, and we can give the hinge length. So we keep this as a default, and I said okay. We also can modify other parameters. Yeah, you can see the data which is giving for us here. And we also can give the this acceptance criteria or the pushover curves criteria, and we can give it. This is the moment yield, so it means when it reaches to the B, and that is the yield point, and this is passing 1.25% more than the yield point, and then again it's going to be reduced and again to reduce, and we can actually calculate this. There is some formula, and also when you have the cross section, so we keep it as a default. The program will calculate automatically, so okay, and also the moment interaction curve also as well, and you can use different code and different equation, so it's okay as a keep it simple. And the second is going to be define the beams, and for the beams also we must select moment measure moment, because the beam will will deform or will yield because of the measure moment. So here is the parameter. This you can be edited, or you can determine manually, and you can change the type of is just type of the hinge. So we have different type. You can use kinematic takeda. When you use this takeda, you must determine the parameters and then properly define. So if I give this, so the program automatically calculate based on the takeda. So I want to use degrading, and we also can change the degradation of the model. So this is the hinge graph. It is symmetric in positive and negative, so we keep it okay. And for the brass, we will use automatic one. Now we select all the beams. We assign frame here, and it is called hinges, and we select beams, and in the end of the beam, which is a distance of 0.1. In other, we usually use 2, 1 in 0.1, and that is 0.9. So apply. Now you can see the hinges appear. So we select the column as well. And here should be the select. And we go back to that sign and frame hinges. The same things this time 0.9 and 1, and we should actually select modify column, and then we're gonna 0.9 another one. So apply, and we have selected, we have assigned the hinges. Now it's time to assign the hinges to the brass. We go again, frame and hinges, and we use automatic, and just we use in the one hinge in the middle of the brass. So we come to the add hinge. Here we have 3 tables. One is the earliest one, 17, and this the latest one is the earliest one, and using the 13. And then we come here, we should select the steel brass, and just it's axial, so the deformation caused by axial force, so we keep it and apply, and we have done. One more thing, we can select all, then we assign a hinge override, so by 0.1. So we have done. Hinge is actually assigned. Now we go to define some loads. So come to the define, and here is called load pattern, and we must define a dead load. The one is self load, and it's called dead load. That means we have an extra superimposed dead load. We come to here, and we call the super dead load without self multiplier, and we also have a live load. And now we have in case if we have some a lateral load, we also can define here as a lateral load, but we just consider the lateral load should be displacement. We will assign this in the pushover cases. So okay. And now we select the beams. And we want to assign the load. That's frame load and distributed load, and it will be dead load, super dead load as a gravity, NSP 10 sign, and you can see a sign, and we also can previous selection, and we changed to the live load, and this be 15. So remember, sometimes the roof will be less, so we accept that's a uniform, and you can consider in your study in case its roof is different. Now you can check here, and here is the load to load. If you want to edit, you also can edit here. You can edit it's 15 and it's 10. Now the load is completed into the sign, and we go to the load cases, and we firstly we don't need to consider the model type or pushover using mode type, so we don't need this, and we want to change the dead load to the nonlinear type, and the live load is also as a nonlinear, and the continue from the state which is going to take the late dead load. So okay and okay, and we have finished already 2 dead load, and then we're going to define the pushover case. It's called pushover. And pushover is nonlinear. In this case, we can considering the geometric nonlinearity parameter as well, or maybe ignore. And come to the here, acceleration is u1, and we want to give a -1 to apply in this direction. So at, and here is some parameter to control the loading. So I used displacement control. You can also use full load control, and I'm going to use displacement control. So the load should be about let's be 1 meter, pushing the structure in the top of this node to 1 meter. And this is joint 6, so it means this this point. And okay, and here is called results should be saved in multiple steps. And nonlinear parameter is also quite important, and you can use different solution scheme and also iteration time. So the maximum total step should be 200. The maximum null step should be 15. This is a default parameter. You can change, and it will affect the analysis time and also the analysis accuracy. So I keep this because it will solve faster. So okay. So okay. Now before that, I'm going to the analysis and see analysis option. So it's a 2D. Use 2D. Okay. And go to the analysis again, and we want to run the analysis. And we don't need model analysis. We're going to offset this and done. So, but before that, we should save the. It's required to save. Yeah, let's save it. We can listen to be here. Yeah, we're gonna go eccentrically class frame. Yes. And the analysis started. 65%. And I should say pushover analysis can be conducted using mood shape. So we didn't use mood shape. Yeah, this is the analysis. The analysis completed, and you can firstly see there is no error in was one warning, so we ignore that warning, and because maybe there's significant deformation, that your error is warning is because of that. So here we come to the pushover, and we can use envelope max, and we're using this one file, and you can see in the maximum we have this one. So the entire column is collapsed, and that means collapse, and this actually that one means collapse prevention, and this one collapse. So the mostly the brasses damage and reach to the collapse point, and the beam is still in the life safety, and column is in the collapse prevention. So we can use steps. Let me use the steps. Come to here, steps, call steps, and it's step 1. In step 1, just we have 1 hinges. Second hinge. This means the hinge location, and second hinge is appeared from life safety to collapse prevention, and we increased the number of step 7, and we can see the first one. This one is collapsed, and we can go further. So 10, 11, 12. So each step. So now we come to the display. 15. We come to the display here. 18, 19. Yes. Yeah, we come to the display, and here is called show static pushover curve, and here is the static pushover curve. Then you can see here the static pushover curve. And this is the maximum 1 meter displacement, and this is the shear base capacity. So then you can actually export here this. You can display the table, and you can plot it anywhere you want. And here is the condition. This is A. This is A to B, and B to C, C to D, and this is IO, which the hinges reach with the displacement to the immediate occupancy, and this is the life safety. Here's immediate occupancy is okay, and it's life safety, and here is we also have beyond collapse prevention, and so many information you can actually export to the Excel, and we also have some other things to get the yield displacement and also yield strength. So we can use compare with the ATC, American Technology Council, this one, and FEMA, and you can compare with FEMA 41 equal organization, and you can get the V and D, and performance point is ACA, which is ACA and ACD, and also you can see the ductility and also the performance point of the period and some other parameter, and we also can use ATC as well, performance point. And so this is the result, and you also can export this data, and you can interpret and get more information about this tutorial. So this is the end of the tutorial. If you have any question, but before that, let me show you one more thing. Show hinge result. Actually, here is the hinge, because the hinge is going to be deformed, so you can select which hinge you want. So I'm going to using the brass, so this is automatic. You can see the plastic deformation. That was step 1. Step 0, you can actually come to the step. This is column. Let me go back to this one, and you can see the parameter, the actual force ratio, this one, and then the point will be here, which is here is the plastic deformation is metered, and also there is the actual force. So you can actually you can see here this data, and hinge state is going to be less than E. E is previously defined in the defined hinge, and also this one also the state collapse prevention is thing. And you also can see the backbone scale. The backbone is going to be like this. So some other information can be find out here. So that's all. If you have a question, please put in the comment, and I'll find time to answer you. See you next time.